Hi everyone. In this video, we're going through May 2024 past paper for Pearson Edexcel International GCSE Physics, paper 1P. Let's look at the first question. Okay, so question number 1. This question is about the motion of objects in the solar system. A1, draw a label diagram showing the moon orbiting the Earth. So let's draw the Earth, and the moon has a circular orbit around the Earth. It's okay if it's not perfectly circular. It's good enough. We should label the moon M-O-O-N. Okay, so we've labeled it. It's fine. Okay, question number 2. Give the name of the force that causes the moon to orbit the Earth. So the only force that acts on the moon is the gravitational force exerted by the Earth. So the answer would be gravitational force. Gravitational force, gravitational force. This force also acts as a centripetal force for the moon, but gravitational force is good enough. Question number 3, give the name of another object that orbits the Earth. So other than the moon, satellites orbit the Earth. We can say artificial satellites, ARTIFICIAL, satellites. Okay. Then question B, a planet and a comet both orbit a star. Give a difference between the orbit of a planet and the orbit of a comet. The main difference between their orbits is a planet has a circular orbit. A planet has a circular orbit, but a comet has an elliptical orbit. Elliptical orbit. So that's question number B. So we're done with question 1. Quite easy. Number 2, this question is about radioactivity. So 2a, the nucleus of an atom of carbon has 6 protons and 8 neutrons. So carbon, atomic number 6, neutron number 8 means mass number would be 6 plus 8, which is 14. Which row of the table shows the nucleus of an atom that is a different isotope of carbon? So a different isotope means the atomic number has to be the same. The neutron number will change. So the number of protons will be the same. Number of neutrons need to be different. So we already have 8 neutrons. So it should be 6 neutrons and 6 protons. The answer should be A. Question number B. Which type of radiation is high energy electron? So out of all of these, beta particles are electrons. So B, beta. Question C. A nucleus emits radiation. This causes the mass number to decrease by 1. Okay, the atomic number stays the same. So if atomic number stays the same, proton number doesn't change. And it also says mass number decreases. That means neutron decreases. So which type of radiation does the nucleus emit? It will be a neutron radiation. Question number D, the nucleus of an isotope of uranium can be represented using this symbol. Okay, uranium-92, mass number 238. The nucleus forms part of a positively charged ion. It's just a nucleus, and it has electrons orbiting the nucleus, but the number of electrons won't be the same as the number of protons as it is an ion. So the number of electrons need to be smaller than the number of protons. So the only option that is suitable is A. There will be 90 electrons, 92 protons. Overall charge would be +2, positively charged ion. Question number E. A radioactive isotope has an initial activity of 400 becquerels. The half-life of the isotope is 8 hours. That means the activity decreases by half after 8 hours. So what is the activity of the isotope after 16 hours? So let's say it starts with 400 becquerels. After 8 hours, the activity should decrease by half, 200 becquerels. After another 8 hours, the activity should decrease by another half. So half of 200 is 100. That means after a total of 16 hours, the activity should become 100 becquerels. So the answer should be C. Now let's move on to number 3. A photograph shows infrared heating lamps being used to harden fresh paint on a car. So infrared heating lamps. Question A, give a harmful effect of infrared waves. So infrared waves can cause skin burns, burns to the eyes, tissue burns. So we can just say infrared waves cause skin burns. Question B. The heating lamps produce visible light waves in addition to infrared waves. Give two similar properties of visible light waves and infrared waves. So both of these waves are electromagnetic waves. So both are electromagnetic waves. We can also say both are transverse waves. But there's one more thing we can say. They both travel at the same speed in vacuum. Both travel at a speed of 3 times 10 to the power 8 meters per second in vacuum. This time we have to give two differences between the properties of visible light waves and infrared waves. So let's arrange everything on a spectrum. So how does it look? The one with the highest frequency is gamma rays. Then we have X-rays. Then the next one is ultraviolet. And we have visible light at the middle, at the center, visible. And then beside visible is infrared, microwaves, and the last one is radio waves. So this is the order of increasing frequency. We can say that visible light waves have a higher frequency, or you can say have higher frequencies. Wavelength decreases when you go from left to right. So infrared has a longer wavelength than visible light. We can just say visible light waves have shorter wavelengths. Question number C. The infrared heating lamps are placed 1.5 meters from the car. Calculate the time taken for infrared waves emitted from a lamp to reach the car. So let's visualize what's happening. So let's say this is a lamp and there's a car a distance away. And this distance is 1.5 meters. Infrared waves are emitted and they will reach the car. The distance is 1.5 meters. Calculate the time taken. We want to find the time. How long does it take for the waves to reach the car? We know the speed of infrared waves, so we can use the wave equation. We can use the speed equation. V equals S by T. So since we know the speed and distance will make T the subject, we'll rearrange the equation. T is equal to S by V. We know the distance, that's 1.5 meters. We know that the speed, 3 times 10 to the power 8 meters per second. This gives us a time of 5 times 10 to the power negative 9 seconds. 5 times 10 to the power negative 9. That's very quick. Let's look at question D. Paint takes less time to harden when it absorbs more energy from infrared radiation. A technician observes that white paint takes more time to harden than black paint. Explain this observation. So we know that black is a good absorber of radiation, whereas white is not. So we can write that down first. So we can say black color is a good absorber of radiation, electromagnetic radiation, whereas white color is not. So why does it take more time? Why does white take more time? That's because black absorbs more energy per unit time. So black absorbs more energy per unit time. Therefore, it hardens faster. It hardens faster than white paint. And number 4, this question is about the evolution of a star. Question A, a main sequence star is created in a collapsing region of a nebula. What is a nebula? Nebula is a collection of gases and dust, hydrogen, helium, gases and dust. And when they collapse, when they get close to each other at high speeds, fusion reaction starts, and that is how a star is born. Okay, So that's what this says. A main sequence star is created in a collapsing region of the nebula. The table gives different energy stores for the gases in the collapsing nebula, from when the nebula starts to collapse to just before the main sequence star is created. So from the collapsing stage to just before the star is created, what energy changes happen? So if we think about it, before a star is created, there's no change in chemical energy. So chemical energy stays the same. What happens to the gravitational potential? Since the gases and dust, they collapse into a center, they move towards a center at high speeds, they get closer and closer to each other. So gravitational potential decreases. What about nuclear energy? So since a fusion reaction hasn't started yet, the nuclear energy wouldn't change either. It'll be the same as chemical energy. Chemical energy, nuclear energy, they don't change. What happens to the thermal energy? So as the particles collapse towards the center, they gain more and more speed, and this increase in speed increases the thermal energy. So the thermal energy will increase. So a decrease in gravitational potential energy results in an increase in kinetic energy of these particles, or thermal energy. Okay. Question B. At the end of the main sequence stage of a star's evolution, the star can become a red giant or a red supergiant. Give the property of the star that determines whether it becomes a red giant or a red supergiant. So that the thing that determines whether main sequence star becomes a red giant or a red supergiant is its mass. So it depends on the mass of the star. Question number C. A red giant star eventually becomes a white dwarf star. White dwarf star. Discuss the differences between a red giant star and a white dwarf star. So a red giant star is quite big in size. There's still some fusion reaction happening inside, so it's still radiating energy outwards. After all the fuel is gone, when the fusion reaction stops, it collapses into a white dwarf. White dwarf star is much smaller in size than the red giant. Let's write down the differences. Red giant star is much bigger in size. What else can we say? We need to state 4 points. We can say that the fusion reaction takes place in red giant star, but it's not there in the white dwarf star. So nuclear fusion does not take place in white dwarf. That's why it does not emit a lot of radiation. So white dwarf is not as bright. So red giant star is brighter than white dwarf. So 3 points altogether so far. We can say that since the white dwarf is much smaller in size, all of its mass is condensed in inside a very small space. So we can say a white dwarf has a larger density. Or we can just say white dwarf is denser. Okay, so these are the differences between the two stars. Okay, let's look at question number 5. A metal spring obeys Hooke's law. Sketch a graph to show that the spring obeys Hooke's law as it is stretched. You should label both axes with appropriate physical quantities. Hooke's law states that the force needed to extend a spring is directly proportional to its extension. So we need force on the y-axis. Force is measured in newtons. We need to mention the physical quantities as well. So force against extension of a spring. This will be measured in meters. So Hooke's law suggests that the force and extension are directly proportional. So that means it'll produce a straight line, and this line will pass through the origin. So this should be good enough. Let's move on to the next question. Question number B. Diagram 1 shows an object suspended from a support using a metal spring. The object is initially at rest. When the object is at rest, that means the forces are balanced. The forces acting on the object would be its weight and the spring force or elastic force balances the weight so that there is no net force and it is at rest. So at this point, elastic force and weight are equal. Question number 1, the object is pulled down and then released. Okay, so what happens is somebody pulls down this object and releases it. So diagram 2 shows the forces acting on the object at the instant it is released. So as soon as it is released, there's a greater extension in the spring. The greater the extension, the greater the force. That's why the elastic force is greater now. It's 3.2 newtons. It's more than the weight of the object, which is 2 newtons. The question is, determine the magnitude and direction of the resultant force acting on the object. So net force equals 3.2 newtons minus 2.0. That gives us 1.2 newtons. And so the magnitude is 1.2 newtons. The direction of the resultant force is upwards. So we should write upwards here. Okay, let's move on to the next question. The object has a mass of 0.2 kg. So the object we looked at has a mass of 0.2 kg. Calculate the acceleration of the object at the instant it is released. So this is the object. The net force, let me just draw the net force on it. The net force acting on it is 1.2 newtons. This object has a mass of 0.2 kg, and we need to calculate the acceleration at this point. So we'll use the formula F equals ma, Newton's second law formula. We want to calculate acceleration. We'll rearrange the equation. A equals F over m. The net force is 1.2 newtons. The mass is 0.2 kilograms. This gives us an acceleration of 6 meters per second squared. So the answer is 6 meters per second squared at this point. So question number 3, explain how the magnitude of the acceleration of the object changes from the instant the object is released until the first time the object returns to its initial resting position. So we need to explain how the acceleration changes between 2 stages. So the first stage is when the spring force is larger than the weight force, and there's a net force acting on it, and it wants to accelerate upwards. When it returns to its initial resting position, the weight and the spring force, they become equal. So 2.0, 2.0. So you can see at this point, there's no net force, so acceleration should be 0 at this point. So this is what we need to explain. As the object is released, the extension decreases. This means the spring force decreases, or elastic force decreases. As the spring force decreases, the net force also decreases, resulting in a decrease in acceleration. By the time the object reaches its initial position, acceleration becomes 0. Okay, now let's move on to question number 6. Diagram 1 shows the magnetic field lines near the south pole of a bar magnet. A, draw 2 arrows on the field lines in diagram 1 to show the direction of the magnetic field lines. So we only need to draw 2 arrows. So we can choose this one and this one. Okay, question number B. Which of these is attracted to the bar magnet if placed in the magnetic field? So only magnetic materials will be attracted, and the magnetic materials that we have learned are iron, nickel, and cobalt. So in these options, we have nickel, so the answer should be B. Copper, plastic, zinc are not magnetic materials, so they won't be affected by the magnet. Question number C. The strength of the magnetic field changes as the distance from the South Pole increases. Explain how the magnetic field lines show this. So let's say we have an object. The further away we move from the magnet, we can see the separation between the field lines, so the magnetic field lines, increases. As the magnetic field lines go further apart, the magnetic field strength decreases. That's what we have to explain. So we can write as the distance from the pole or south pole increases, the felines get further apart from each other, indicating a weaker field strength. Question number D. Diagram 2 shows a small piece of iron that has been placed in the magnetic field. Explain why the piece of iron experiences a force towards the south pole of the bar magnet. Why does it feel a force in this direction? You may add to diagram 2 to help your answer. So we know that the magnetic field lines have arrow direction pointing to the south of the magnet. And if this iron is placed within this field, the orientation of magnetism will be the same as the field lines. So what does this mean? The side where the arrowhead lies is the north pole, and the side where the tail lies is the south pole. And you can see the north pole of the iron faces the south pole of the magnet, and opposite poles attract each other. That's why this iron bar feels a force towards a magnet. So that's what we have to explain. So we can say a north pole is induced on the side nearest to the magnet. North pole is induced on the side nearest to the magnet. So as opposite poles attract, the iron feels a force towards the magnet. Question number 2. A student suggests that the piece of iron is now a permanent magnet. Explain why the student is incorrect. So iron is magnetically soft. So iron is magnetically soft. What does that mean? If we move this iron away from the magnetic field, iron will lose its magnetism. So we can say it loses its magnetism when it is removed from the magnetic field. Okay, that's the end of question 6. Now let's look at question 7. Question 7. The diagram shows a domestic lighting circuit. So we can see this is a parallel circuit with 3 lamps and 3 switches. Explain an advantage of using this circuit for domestic lighting. The advantage is that the lamps can be independently switched on and off. So let's write that down. The lamps can independently be switched on or off. Why is that? So explain. We have to explain this advantage. Why? It's because they're connected in a parallel circuit. So we can say that lamps can independently be switched on or off because they are connected in parallel. Okay, number B. When switch 1 is closed, the current in lamp 1 is 22 milliamperes. So let's have a look. So when switch 1 is closed, it is closed at the moment. The current in lamp 1 is 22 milliamperes. Give the name of the charged particle that moves in an electric current. So it is the electrons that move in an electric current. So we can write down electrons. Question number 2. Show that the lamp 1 has a power of about 5 watts. So what is power? How do we calculate power? Power is equal to, in this context, it's going to be voltage times current. But generally, power is the rate of doing work. So do we know the voltage of lamp 1? We know the current we just saw. What is the voltage across lamp 1? So if we look at the circuit, since it's a parallel circuit, all the lamps have the same voltage as the mains voltage, 230 volt. So the voltage is 230 volt, the current is 22 milliampere. So power equals 230 volt times 22 milliamperes. So milli means 10 to the power negative 3. Gives us 5.06 watts. So yes, it is about 5 watt. But we don't need to show that this is equal to 5 watts. We can just round it to 2 significant figures. So 5.1 watts. Question number 3. Calculate the energy transferred by lamp 1 when it is on for 30 seconds. So if this lamp is on for 30 seconds, what's the energy transferred? So energy is equal to Since power is the rate of doing work, P is equal to energy over time. So E is equal to power times time. So power we just calculated is, let's use 5.06 because it's not rounded, times, it's going to be switched on for 30 seconds, gives us 151.8 joules. Again, we can round this to 2 or 3 significant figures. Let's go with 2 significant figures here, 150 joules. Question number C. The circuit is connected to the main supply. Mains voltage is 230 volt. State what is meant by the term voltage. In terms of equation, voltage is equal to work done per unit charge or energy transferred per unit charge. So how do we write it? We can say voltage is defined as the energy transferred per unit charge. We can also include the equation V equals E over Q. Some people use delta E, energy transferred per unit charge. Number 2, switches 1 and 3 are closed, which turn on lamps 1 and 3. Switch 2 is open. If switch 2 is open, lamp 2 will not work. Calculate the current in the main supply. What's the overall current in the main supply? Let's have a look. Switch 2 is closed. Sorry, switch 2 is open. So there won't be any current in lamp 2. Lamp 2 won't be working. So we know that the current in a parallel circuit splits when the wire is split. So at this junction, before the current enters the junction, let's say it comes from the mains voltage, and just before it enters the junction, it has the overall current IT, and then it splits into 2 different paths, one towards lamp 1 and the other towards lamp 3. Let's name them I1 and I3. So I1 is 22 milliampere and I3 is 17 milliamperes. So the total current would be I1 plus I3 in this situation. So we'll say the total current IT is equal to I1 plus I3, where I1 is 22 milliamperes, I3 is 17, and that gives us 39 milliamperes. That's the overall current in the main supply. So let's look at question number 8. The diagram shows 2 rays of light, A and B, incident on the boundary between air and water. From the light source, there are 2 rays, A and B, going towards the air-water boundary. What do we need to do? Let's read the question. The refractive index of water is 1.33. So let's just note that down. N equals 1.33. Explain the paths of the 2 rays of light after they strike the boundary between air and water. So we need to explain what happens to the rays after they strike the boundary. So we know that because air and water have different optical densities, the rays will refract, they will bend at the boundary. So we'll have to explain it. But it also says include calculations in your answer and draw on the diagram to support your answer. So let's start by checking the angle of incidence for both the rays. So first of all, we'll have to draw the normal line at the point where the ray strikes the boundary. And we need to make sure that the normal line is perpendicular to the surface. So that's for ray A. And then there will be another normal line for ray B. Let's mark the angle of incidence. Let's measure the angle of incidence. I've already measured the angle of incidence for ray A, and this is 36 degrees. Make sure this angle is between the incident ray and the normal line. The angle of incidence for B, I've already measured this. This is 60 degrees. Right, so we expect the rays to bend after they enter the water. So we don't expect the rays to move straight. We need to find out at what angle they will be bending, the angle of refraction. So let's calculate that first. So the formula to calculate the angle of refraction would be N equals sine I over sine R. We can use this formula when a ray travels from air to any other medium. We need to know the refractive index of the medium, which is n here. We know the angle of incidence. We know the refractive index. We need to find the angle of refraction. So let's do it for A. For ray A, let's find what sine R is equal to. So sine R will be sine I over n. R would be equal to sine inverse sine I over n. So I'll just substitute the values for angle of incidence. The angle of incidence for A is 36 degrees. The refractive index is 1.33, the refractive index of water. So let's calculate this. Make sure your calculator is in degree mode. This gives an answer of 26.2 degrees. So it has decreased from 36 degrees. Let's do the same for ray B. We can just say R is equal to sine inverse. The angle of incidence for ray B was 60 degrees. So 60 degrees divided by the refractive index of water is 1.33. And this gives us a value of 40.6 degrees. So we can draw the path. So the angle of refraction for ray A would be 26.2 degrees. And the angle of refraction for ray B would be 40.6 degrees. So we can see that it's going to be less than the angle of incidence in both cases, both ray A and ray B. The angle of refraction is smaller than angle of incidence. That means the rays will bend towards the normal. And it makes sense because air has a lower optical density, water has a higher optical density. So the ray should bend towards the normal in this case. So you'll have to measure the angle of refraction from the normal line and draw the refracted ray. So this angle would be 26.2 degrees, and we'll do the same for ray B. The refracted ray will bend towards the normal. Angle of refraction here is 40.6 degrees. So okay, we have drawn the diagram. We have included the angles. We've done the calculations. We need to explain now. We'll be given 6 marks on this. We need to explain why refraction happens, why the ray bends when the rays enter from air to water. So we can say that water has a higher optical density than air. And this means that light travels at a slower speed in water than air. So if light travels at a slower speed in water than air, the ray of light needs to bend. That's why refraction of light occurs, and that will be enough. So we'll get 1 point for water has a higher optical density in air, another point for light travels at a slower speed in water than air. We'll get marks for calculating the angle of refraction, and we'll also get marks for accurately measuring the angle of incidence for both the rays. So that'll be 6 marks in total. Okay, let's look at number 9 now. This question is about air pressure. Question A, during an aeroplane flight, a passenger drinks some water from a plastic bottle. The passenger then replaces the top to seal the bottle as shown in diagram 1. The air pressure outside the bottle is 80 kPa, which is less than the atmospheric pressure on the Earth's surface. So the question is, state the air pressure inside the bottle just after the bottle has been sealed. So all of this is happening during an airplane flight. If somebody drinks water from the bottle, they need to open the cap. And if the air pressure in the airplane is 80 kPa, the air pressure inside the bottle also becomes 80 kPa when the cap is open. And when the top is closed and sealed, the air pressure inside the bottle remains 80 kPa. So the answer should be 80 kPa. The air pressure inside the bottle just after the bottle has been sealed is 80 kPa. Let's look at question B. As the airplane descends, the air pressure inside the aeroplane changes. When the airplane lands, the passenger notices that the plastic bottle has collapsed. as shown in diagram 2. Explain why the bottle has collapsed. So first thing we should say is, as the airplane descends, the pressure in the airplane increases. That's the first thing we should say. So as the airplane descends, pressure in the air pressure in the airplane increases, while the air pressure inside the bottle remains at 80 kPa. So outside the bottle in the airplane, the pressure is higher than 80 kPa, but inside the bottle, the pressure is 80 kPa. So what will happen is that the greater air pressure outside the bottle will exert a resultant force on the bottle, and this will make the bottle collapse. So we should say, so there will be a resultant force acting on the bottle from the air molecules outside, and this makes the bottle collapse. That should be enough for 2 marks. Question C. Explain how the gas molecules in the air exert a pressure on the surface of the bottle. 3 marks are given. So let's think about this. So we know that the air molecules are randomly moving all the time. The air molecules move in a random direction all the time. That's the first point. Then we can say these air molecules collide with the surface of the bottle. As they collide, they exert a force on the surface of the bottle. And according to the definition of pressure, since pressure is equal to force divided by area, the air molecules exert pressure on the bottle overall. That should be enough for 3 marks. Okay, let's look at question 10. Diagram 1 shows the apparatus a student uses to investigate the bending of a wooden strip. So we can see this is a table. We can see the wooden strip that is bent here. Part of the wooden strip is clamped to a table. A load is fixed to the free end of the wooden strip. Yes, there's a load at the free end, and this load causes it to bend. The free end of the wooden strip is positioned at length L beyond the edge of the table as shown in diagram 1. The length of the strip beyond the table goes from here to there. A student investigates how the length L affects the height h. So this length L, how does it affect height h? So question A, the load has a mass of 250 grams. So the load that is put there has a mass of 250 grams. We need to calculate the weight of the load. So weight is equal to mass times gravitational field strength. So we'll say equal to, but we need to be careful. Mass has to be in kilograms. So 250 grams is equal to 0.25 kilograms times the gravitational field strength would be 9.8. This gives us 2.45 newtons. We can round this to 2 significant figures, so 2.5 newtons. So question B. This is the student's method for the investigation. Clamp the wooden strip so that L is equal to 20 cm. Fix the load to the end of the wooden strip, as shown in diagram 1. Okay. Measure the height h. So we fix the L value, the length that is beyond the table, and we measure the height h. Okay. The student repeats this method for different values of L. So the student will change L to a different value, and then he will measure the height accordingly. So question 1, give the independent and dependent variables in this investigation. So the variable the student is actively changing is the length of the wooden strip beyond the table, L. So that's the independent variable, length, L. What is the dependent variable? So after changing the length, he measures the height. This is the dependent variable, height. Question 2. Give 2 control variables in this investigation. So as the student changes length, the height changes and he measures the height. During this entire process, he needs to make sure few things are kept constant. So we need to make sure the mass of the load stays the same. So number 1, the mass of the load stays the same. The second one is the position of the load. We need to make sure it stays at a fixed position. So the position of the load. Number 3, suggest how the student could accurately measure the height h. So let's look at a diagram. So in order to accurately measure the height h, the student could fix a ruler at the end of the strip, maybe by clamping it with something, with a clamp stand, and also aligning the 0 on the ruler with the height of a table. And the height caused by bending can be measured by the ruler. So we should say a meter rule should be clamped at the end of the wooden strip so that it is fixed and it doesn't move. The 0 on the ruler can be placed at the height of the table so that any change in height due to bending can be easily read from the ruler. Question C. The table shows the results of the investigation. So the student changed the length from 20 to 40 and many other values. And for each of these length values, the student measures the height due to bending, which also changes. Diagram 2 shows the wooden strip when the length is 80 centimeters. So when length is 80 centimeters, in the table, we don't have the height yet. Using diagram 2, determine the height h in the laboratory. This is a scale diagram. It has mentioned the scale. 1 centimeter on the diagram is equal to 10 centimeters in the laboratory. So we need to measure the height using a ruler. This should be around 3.1 centimeters. So if it's 3.1 centimeters on the diagram, in the laboratory, the height would be 3.1 times 10. 3.1 centimeters on the diagram would be 31 centimeters in the laboratory. 31 in the table and there as well. Okay, question number 2, plot a graph of the student's results. So using this table, we can put the plots on the graph. But before we put the plots, we need to decide the scale. So our maximum value for L is 120, starts from 20. Let's see. For L, we can set this point to be 0. This could be 20, 40, 60, 80, 100, and 120. Whenever we draw graphs in the exam, we need to make sure we use more than 50% of the area that is given to us. The height, what's the maximum height? The maximum height we can see is 71. Starts from 2, ends at 71. So let's choose a suitable scale. We can make this 20. This can be 40. This will be 60. And this would be 70. Now we need to plot the points. The first point, when length is 20 centimeters, the height is 2 centimeters. So if 10 small squares are equal to 20 centimeters, one small square would be 2 centimeters. So that means here is our first plot. The second plot is when the length is 40 centimeters, the height is 8 centimeters. So 8 centimeters would be here. When length is 60, the height is 18. 18 would be here. When length is 80, the height is 31. So since 30 would be here, 31 would be right above that point. When length is 100, height is 53. So 50 is here, that is 52. 53 would be there. Last one, when length is 120, height is 71. 71 would be here. So since we have plotted the points, question number 3 says, draw the curve of best fit. So when we think about the best fit curve, the plots show that it's not going to be a straight line. It should be a curve. So let's ensure that we draw a nice curve passing through almost all the points. Maybe you can do a better job. That's not too bad, but I think when you do it on the paper, you can draw a smoother line than this. Number 4, a student concludes that H is directly proportional to L. We need to evaluate the student's conclusion. For H to be directly proportional to L, we need a straight line. We didn't get a straight line. That means the student is wrong. So we'll say for H to be directly proportional to L, we need a straight line on the graph. Since we obtain a curved line on the graph, H is not directly proportional to L. The student's conclusion is incorrect. Okay, let's look at question 11. The photograph shows a power bank used to recharge the battery in an electronic device. Question A. The power bank stores charge. The charge stored can be measured in amp hours. 1 amp hour is the amount of charge transferred by a current of 1 ampere in a time of 1 hour. Calculate the charge stored in coulombs when the charge stored is 1 ampere hour. 1 ampere hour is the amount of charge if it is charged with a current of 1 ampere in a time of 1 hour. How are charge, current, and time related? It's given by the formula Q is equal to current I times T. We need to calculate the charge stored. Q is equal to, so current will be 1 ampere over a period of 1 hour. We need to convert 1 hour into seconds, which is the SI unit of time. 1 hour has 3,600 seconds. That's why the total charge stored in this power bank would be 3,600 coulombs. And 3,600 coulombs is equal to 1 ampere hour. Okay, question B. An electronic device is connected to the power bank. Whilst recharging, the electronic device receives a constant current of 2.4 ampere and 3.8 times 10 to the power 3 coulombs of charge is transferred. Calculate the time taken to recharge the electronic device. So we know the current, we know the charge Q, we need to find the time. So we'll use the equation again. Q is equal to I times T. This time we need to find the time taken. So T is equal to Q over I. So the amount of charge transferred is 3.8 times 10 to the power 3 coulombs, which is already an SI unit, divided by a current of 2.4 amperes. How long will this take? This gives us 1583.3 seconds. But they want the answer in minutes, so we'll divide this by 60. So 1583.3 divided by 60 minutes gives us 26.3 minutes. And if we round this to two significant figures, that is approximately 26 minutes. So it'll take 26 minutes to recharge the electronic device. Question number 3. The electronic device is connected to the power bank using a long cable. Suggest how using a long cable affects the time taken to recharge the electronic device when compared with a short cable. So what's the difference? Long cable, short cable? We know that using a long cable will have a higher resistance. Let's write that down. A long cable will have a higher resistance. This will decrease the current. This will decrease the current. So if the current is decreased, how is the time affected during the charging process? So let's use the equation again. Q equals I times T. Let's make T the subject of the equation. T is equal to Q over I. So what's the effect on time if current is decreased? So you can see if the denominator is decreased, the overall number will increase. That means the time will increase. So it'll take a longer time. So Therefore, using a long cable will take a longer time to recharge the electronic device. Question C. So a student uses 3 electronic devices. Each electronic device stores a different amount of charge. The table gives some information about the charge stored by the electronic devices and how often they need to be recharged. So we have 3 devices, A, B, and C. Device A stores a charge of 2.4 ampere hours. Device B is 4.2. Device C is 6.8. So device C stores the highest amount of charge. The frequency of recharging, how often are these devices recharged? So device A is recharged once every day. Devices B and C are recharged once during the week. Let's continue reading the question. The power bank stores a maximum charge of 26.8 ampere hours. The student needs to take these 3 electronic devices on a school trip for 1 week. Determine whether the maximum charge of the power bank is enough to recharge the batteries of the 3 electronic devices during the school trip. So the student is going on a trip and the trip will last 1 week. We need to calculate whether the power bank can recharge all of these devices. So let's calculate what's the total charge required by the devices over the 1 week period. Total charge required is equal to device A requires 2.4 ampere hours of charge, but this needs to be recharged every day for a week, so times 7, plus device B needs a charge of 4.2 ampere hours just once in a week, plus device C needs 6.8 ampere hours of charge once in a week as well. So in total, the total charge required over the week would be 27.8 ampere hours of charge. Maximum charge of the power bank stored by the power bank is equal to 26.8 ampere hours, which is less than what is required, 27.8 ampere hours. Let's read the question again. The question says, determine whether the maximum charge of the power bank is enough to recharge the batteries of the 3 electronic devices during the trip. So obviously, that's not enough. The maximum charge of the power bank is not enough to recharge all the devices during the school trip, assuming they are recharged from 0 battery percentage. But this is unlikely. It is unlikely that all the devices will have 0 battery percentage at the start of the trip. So we can say, however, the devices might not be at 0 battery percentage at the start of the trip. So maybe the power bank will do the job. This last point is extra because 4 marks will be awarded. It's safer to add an extra point here. Okay, number 12. A car accelerates with a constant driving force along a horizontal road and reaches its maximum speed. This is the velocity time graph for the car's journey. So on the y-axis, we have velocity. X-axis, we have time. Question A, by drawing a tangent to the curve, determine the acceleration of the car at a time of 20 seconds. So we need to determine the acceleration of the car when the time is 20 seconds. This is where it is on the graph at 20 seconds. We need to determine the acceleration at this point. Since this is a velocity time graph, the gradient of a velocity time graph gives acceleration. We need to find the gradient of the graph at 20 seconds. And since this is a curve at 20 seconds, we need to draw a tangent line first. So let's see how we can draw an accurate tangent line. So I will try and draw a straight line around the point, and I'll draw it in a way that the area between the curve and the line looks symmetrical on either side of the point. So something like this looks symmetrical. Now you can do this with your ruler, and then we can move this line right on the point. And we can still adjust a little bit. So we need to make sure that the distance between the line and the curve is symmetrical on either side of the point. Now this looks fairly symmetrical. We have the tangent line. How do we calculate the gradient? So we'll choose 2 points on the line that can be read easily. So I'll choose this point here, and I need to choose another point, maybe this point. We need to calculate the rise and the run in order to find the gradient. So what's the rise going from point A to point B? So what's the run? Let's start with the run. So it needs to run this much, and then it needs to rise this much. So let's see what is the run value. So each small square has a value of 2. So this is 50, that's going to be 54. What about this point here? Since this is 10, that's going to be 8. So the run is 54 minus 8, which is 46 seconds. Since I'm reading the x-axis, let's calculate the rise. What's the rise? So here the value would be 24. Each small square has a size of 2. So that's going to be 70, 72, 74. So the rise is 74 minus 24. And that gives us 50 meters per second. So what's the gradient? So we can say acceleration equals rise by run. We need to make sure we show all of this on the graph. We show this triangle on the graph to calculate the gradient. So what is rise? We found the rise to be 50. The run is 46. And that this gives us 1.086 meters per second squared. So if we divide meters per second with seconds, we'll get meters per second squared. And if we round this to 2 significant figures, that's 1.1 meters per second squared. So that's the acceleration of the car when the time is 20 seconds. Question B, determine the distance traveled by the car during the first 80 seconds of its journey. In order to calculate the distance traveled from a velocity time graph, the area under the graph gives us the distance traveled. So let's look at a graph. So we need to find the area up until 80 seconds. And we can see this is not a regular shape. There's a curve involved. So how do we do it accurately? So we can fit a trapezium in this shape. A trapezium looks suitable here. So how do we do that? I'll draw a horizontal line at the top at 64. I'll draw a vertical line at 80 seconds. And then I'll draw a line from the origin. I need to decide at what point should I put this line to form a trapezium shape. So let's say I put the line right here. I'll explain why I did this. So I'll reduce this line, the length of this line, so that it looks like a trapezium now. The reason why I drew this trapezium like this is because we are losing this amount of area, this amount of actual area, and we are gaining an equivalent amount of area that we lost in the curve. We can readjust the line maybe this much. So the amount of area we're losing is equal to the amount of area we're gaining, roughly equal. This will do the job. So in order to calculate the area, we need to know the formula of the area of a trapezium. The formula is half times A plus B times height. So this side is A, this side, the opposite side is B, and the distance between these two parallel lines is height, h. Value of B, by the way, is 80. That's simple. It goes from 0 to 80 seconds. The value of A will be, we can measure A from here, which is 42. 42 up until 80. So it's 80 minus 42. This gives us 38. What about h? H goes from 0 to 64. So h is 64. So let's substitute all of these values. So half times 38 plus 80 times 64. A is measured in seconds, B is measured in seconds, H is measured in meters per second. So this becomes half times 118. So since A and B are measurements of time, they are seconds, 118 seconds, times 64 is velocity, meters per second. So if we multiply meters per second with second, the seconds cancel. We're just left with meters. So that's how we get distance from this. And that gives us 3,776 meters. And we can round this to two significant figures, and that gives us 3,800 meters. That is the distance traveled by the car in the first 80 seconds. So you can write all of this in the space provided under B. The distance is 3,800 meters. And we'll get 5 marks on this. Okay, question C. Explain the motion of the car after 80 seconds. So what happens after 80 seconds? We can see the velocity does not change. It stays at 64. It becomes constant. So the car moves at a constant velocity after 80 seconds. Why is that? The question said, a car accelerates with a constant driving force along a horizontal road and reaches its maximum speed. So the car maintained a constant driving force. Why does the car reach a maximum speed? And it reaches a constant speed. Why is that? So first of all, we can say after 80 seconds, the car travels at a constant velocity of 64 meters per second. Now we need to explain the motion of the car. Why does this happen? So this shows that acceleration is 0. This means the acceleration is 0. For acceleration to be 0, the net force on the car needs to be 0. The resultant force on the car becomes, or you can say is 0 at this point. Why is that? That's because even though the car maintained a constant driving force, the resistive forces like air resistance, they keep on increasing up to the point they equal the driving force. So let me draw a diagram. So let's say this is a car. Initially, it has a big driving force, but it has a small air resistance or resistive forces. So as the speed increases, friction stays the same, but air resistance also increases with speed. So there will be a point that air resistance increases to a point where it matches the driving force. And this is where the net force becomes 0 and the acceleration becomes 0. We can just say that at this point, the air resistance acting on the car increases and becomes equal to the driving force. And that should be enough. Okay, this is the end of paper 1.